that you have studied range. So you first studied range and then you studied IQR. These measures of dispersion are independent of the measures of central tendency. Their definition does not involve the measures of central tendency, mean or median or mode. So it would be important to see how you can introduce a measure which takes into account the mean observation as well, and then it talks about the spread of each observation from the mean. So let us see, suppose here it was your data set and you had certain observations. So range was doing what? So range was just the difference between these two endpoints. It was just taking the difference between the maximum and the minimum. Now, what was IQR doing? IQR was saying that, let us suppose IQR was considering that, okay, somewhere here, and it is this side, so Q1 and Q3. So it was looking at the difference between Q1 and Q3. However, it would be interesting if suppose some observation is here at this point, likewise you have some observation at this, and you look at the distance of each observation from the mean this way. And this is basically your mean. So if these are xi's, suppose this is x1, x2, x3 and so on. So you are basically looking at the difference between these two. So mean we denote by mu. So we are looking at the distance between each observation and mu. So which is basically I can write xi minus mu. Now if you see over here, if I just simply add these x1 minus mu and x2 minus mu's, like suppose here x1 minus mu and so on up till x6 minus mu, if I just simply add this, some of the terms might get cancelled because here you will have some negative observations and positive observations. So in order to eliminate that possibility, we just take a square of these observations. We then sum up this and we divide by this n. 1 over n summation xi minus mu whole square, and that is basically your variance. Now note that we will refer to it as the population variance. And so mean is denoted by mu and variance is denoted by sigma square. So these mu and sigma square, we will later on refer to them as the population mean, population variance. And we will have a different notation for the sample mean and sample observations. So you could better write, because for sample size, for population size, we use capital N. So if you just write capital N over here, then it would make more sense, because we are talking about population variance. Okay. And variance, we know that standard deviation, that is sigma, is just the square root of your variance. Okay. And why it is important to quote sigma instead of variance? That is also an important thing to remember, because if suppose you have the data points and you suppose it is the height of the individuals, measured the height in centimeters, so all the observations are in centimeter, and then you calculate the mean, so mean will again be in centimeter. When you calculate the variance, because there is a square over there, it becomes centimeter square. And if you take standard deviation, this will again come back to centimeter only. So that is why you see that the observations were in centimeter, mean is in centimeter. So it makes more sense to consider standard deviation instead of variance, because for interpretation purpose, it would make more sense that it has the same unit as the observations itself. Now, standard deviation can be further understood by considering, suppose you have such a data set over here and you plot it. So here it is 0. Here you have -1, 1 and 2. And this one is 1, 2. Which is again looking like this, having the same shape. But here suppose you have 9 here, and then you have 5 and 1, and this side you will have 13, 17 and so on. So if you want to compare the standard deviations, although this does not look like a perfect shape, but somehow, and you have the standard deviation, want to compare and understand the standard deviation, because standard deviation is what? It will give you an idea about the spread of the data around the mean. So it means by just looking at the value of sigma, you should be able to visualize your data set, that how is it going to look like. In this case, if you see, your data set is here, okay? Here, if you notice that they are on different scales, and you cannot essentially make a comment over here that with sigma, suppose this is sigma 1 and this is sigma 2, which is larger or not. In order to do that, what we can So now what you see over here, that these observations are not very far away from the mean over here, because mean in this case was 0. But in this case, the mean was 9, and here you see the spread is more. So it tells you that if your sigma, if you look at your standard, if you look at the graph, then if it is very much close to the mean, then you can identify that your standard deviation is going to be less. But if it is spread out, then it means that your standard deviation, that is the variance, is going to be more, because it is more spread out around the mean. Likewise, if you find that one sigma is given to you as 1 and the sigma 1 is there and sigma 2 is suppose 4, then by just looking at this, you can understand that the one which has a higher standard deviation, in that case, the observations are going to be more far away from the mean as compared to the first one. So we talked about range, we have seen what is the formula for that, and then we have seen a IQR, and then now we have seen the variance also. And now we are more dissecting into this variance thing, okay? And we are trying to understand and interpret the meaning of this. So the formula is there, right? 1 over n summation xi minus mu whole square. And standard deviation is just basically taking the square root of that. But one wants to understand what is the meaning of this standard deviation. So that is why I just depicted it using this graph over here. And now let us see a standard rule of thumb which says that, which is the rule is referred to as 68, 95, 99%. So it says that if you have a bell-shaped data set, that is, it follows a symmetric distribution, then this is your mean, right? Mean is in the middle. If you add some standard deviations, mu plus sigma here you get, and here you will get mu minus sigma. Likewise, you can add twice of standard deviations. It will be mu plus 2 sigma. Here you will have mu minus 2 sigma. Likewise, you will have mu plus 3 sigma and mu minus 3 sigma. The rule says that if you look at this area between mu minus sigma and mu plus 2 sigma, then in this limits, your 68% of the observations would lie. Now, when you move further away from this, that is, you go to mu minus 2 sigma and mu plus 2 sigma, within this, 95% of the observations would lie. And if you go to the extreme ends, then it would be 99.7% of the observations would lie. So whenever your data set which is given to you, that it is having a symmetric shape or a bell-shaped data, then in that case, remember that 68% of the observations would always lie between mu minus sigma and mu plus sigma. If you go from mu minus 2 to mu plus 2 sigma, then 95% of the observations will be there. And if you go further, then you will get 99.7. Now, one might feel that, okay, why not go further ahead? Because see over here, only 0.3% is left anyway. One can go to mu plus 4 sigma and mu minus 4 sigma, but those things we do not come across in our day-to-day life or in practitioner's point of view. It only appears in your high-level precision experiments. So we do not focus on them, we just look up till mu minus 3 sigma and mu plus 3 sigma limits. So we have talked about pth percentile, we have written the first quartile, second quartile and third quartile. Then we have gone to study about IQR, which is the difference between 75th and 25th percentile. And we have also seen that it is a robust measure because it is not affected by the extreme observations. And then we moved on to study the variance. So as we have discussed this formula, and the standard deviation is in this way. And I was just talking about this standard rule of thumb. So you can see this figure over here, which says that 68%, 95% and 99.7% observations lie in this way. To understand this, let us quickly take a small example. Suppose you have collected data on the height of adults in a particular city, and you have found that the heights closely follow a normal distribution with a mean of 170 centimeter and a standard deviation of 10 centimeter. So this is mu and sigma. Okay, mu and sigma is given to you, and you also know that it is coming from a normal population. Now the question is that what percentage of adults would have heights between 160 centimeter and 180 centimeter? To answer this, the example says that mu is given to you as 170 and sigma is given as 10, right? And it wants to find out what is the percentage that lies between 160 and 180. Now, if you look over here, what is mu minus sigma? Mu minus sigma is in fact 160, and if you take mu plus sigma, then you get 180. This shows that we can use the standard rule of thumb, which says that 68% of the observations lie between mu minus sigma and mu plus sigma. So here also you can say that from the data set that you have for the heights of individuals, 68% of them would have heights between 160 and 180 centimeter. Okay. And now if you see over here, so here basically you have this as 170, here you have 160, and here you have 180. Okay. And this is the mean over here. So this is basically your mu minus sigma, and this is mu plus sigma. Okay. So 68% of observations lie between this. Now, if you want to just see what percentage lie between 170 and 180, so what will you do? In that case, since it is a symmetric distribution, it will be equally distributed on both the sides. So 68 means in between this you have 68%. Here this is 68, right, overall. So it means the remaining, this side, it will be 34%, and this side also it will be 34%. So 34% observations would lie, or the data points would lie between 170 and 180. Similarly, between 160 to 170 also 34% would lie. What percentage of adults have heights between 160 and 180? So we found that it is, since it is one standard deviations above and below the mean, it will be 68%. And if you want to find between 170 and 180 now, so what it will be? It will be half of the adults, so 34% would fall here. Between 160 to 170 and between 170 to 180, the rest 34% would lie. So this is basically for your those populations which are normally distributed. So as you have already seen that the heights follow normal distribution, that is why you were able to apply the standard rule of thumb. Now the question comes up, what to do when your data set is not normally distributed, or it does not have a bell shape, rather it follows some other shape. Except normal distribution, it will have any other distribution. Then in such cases, how can I tell that what percentage of data falls between these two endpoints or not? To answer that, we have a result by Chebyshev. At least 75% of all the values would lie between plus minus 2 standard deviations from the mean, regardless of the shape of the distribution. So whatever is the shape of the distribution, if you look at mu minus 2 sigma and mu plus 2 sigma, then 75% of the observations would lie between these 2 points. And how do we get this? Let us consider. The Chebyshev's theorem says that if you have a random variable x with mean mu and finite variance sigma square, then probability that mod of x minus mu, this is greater than equal to some alpha, this probability is going to be less than variance of that random variable divided by this square. So what it is saying? It is basically giving on the this probability, right? And what is this probability over here? This event inside the bracket, if you see, it is basically saying that the distance between x and mu should not be greater than alpha, right? So it is basically finding the probability that the distance between these 2 points is greater than alpha or not. If variance is small, if this quantity is small, then this probability is also going to be small. The probability is small, it means that probability of this event happening is going to be small, which means that x is going to be close to the mean. So the observations are going to be close to the mean. And that is what we have seen just now also, that if the variance is less, then the observations would be near the mean, right? They would not be spread far out from the mean. So the theorem also gives you the same answer. And now in this inequality, if you just put, suppose alpha you take as k sigma, then mod of x minus mu, you substitute over here. So variance of x I can also write as sigma square, and in the denominator you would have the same thing, whatever constant over here, so that is coming sigma, that square is coming in the denominator, so it will be sigma square k square, which is basically 1 over k square. Now this is the probability of it being greater than k sigma. Now if I want to see mod of x minus mu is less than k sigma, then if I want just the opposite of this, so it means 1 minus of that, so it will be greater than equal to 1 minus 1 by k square. Okay, and this is what we want, because here see k cannot be 1, because that means this right hand side will be 0 in that case. For k is equal to 2, what you get on the right hand side? So let us see what is on the left hand side. It says that x minus mu is less than 2 sigma. This probability is going to be greater than 1 minus 1 by 4, which is basically 1 by 4 is 0.25. So this is 0.75, right? This is 0.75, and if you expand the left hand side, what it gives you is that x falls between mu minus 2 sigma and mu plus 2 sigma. This probability is at least 0.75, or you can say that at least 75% of the observations fall between mu minus 2 sigma and mu plus 2 sigma. And this is what your result over there mentioned. Now you can change the value of k to 3 also. So if you substitute k as 3, then what will you get? So you can see here 1 minus 1 by 9 will be there. So it will basically be coming out as right hand side will be basically this side. Your equality will be 0.88 and this side it will be mu minus 3 sigma less than x. So we need these two only, because this is the statement of the theorem, that at least 75% of the observations would fall between mu minus 2 sigma and mu plus 2 sigma. And likewise, at least 88% would lie. As if you compare it with the normal distribution, that standard rule of thumb, so there you have 68 between mu minus sigma and mu plus sigma, and then between mu minus 2 sigma and mu plus 2 sigma, it is 95%. Although we are unable to reach to that limit, but it is saying that at least 75%, and at least is coming because of this inequality, that this probability will be greater than or equal to 0.75, which means that at least 75% of the observations would lie in 2 standard deviations, plus minus 2 standard deviations from the mean, regardless of the shape of the distribution. So, as you can see over here, specifically for k greater than 1, at least 1 minus 1 by k square of data lies within plus minus k standard deviations from the mean, regardless of the shape of the distribution, and that is what we saw just now. For k is equal to 2, 75% would lie, and for k is equal to 3, 88.9% would fall between mu minus 3 sigma and mu plus 3 sigma. To see an application of this, you can consider that if you are a sales manager for a new product in a retail store and you want to analyze the sales data, and the average sales for this product is rupees 1000 with a standard deviation of 150, what percentage of days had sales between 700 and 1300? If you want to find out this, then you can immediately first of all identify that what is mean, mu and sigma given to you. Mu is 1000 and sigma is this 150. Now it is asking between 700 and 1300. Note that no distribution has been given, so it can have any distribution. So 700, you get 700 from this if it is mu minus 2 sigma, because 1000 minus 2 sigma, that is 300, would give you 700. Similarly, 1000 plus 300 would give you 1300. So you can see mu plus 2 sigma is 1300 and mu minus 2 sigma is 700. So this can immediately tell you by using the Chebyshev's theorem that at least 75% lie within this given range. Okay, so if you are given a normal distribution, then you could go ahead with the normal standard rule of thumb that is given. Otherwise, if you have if the shape of the distribution is anything else, then also you have the result by Chebyshev, which can be applied.